let's start on with the discussion on the concrete data set. It's an exercise that we uh, gave all of you, and we'll quickly have a discussion on this right now. So once again, what you can do is you can log into Colab and you can access the solution file that I've already shared with everybody. So this is the data set, and you can see this. We have got all the different features of concrete: cement, slag, ash, water, superplastic, coarse aggregate, fine aggregate, age. So these are the 8 different features of concrete that we have. And based on the 8 different features of concrete, we are trying to predict what is the strength of concrete. Okay, so here we have the 8 different features of concrete. And based on the 8 different features of concrete, we are trying to predict what is the strength of concrete. So cement, slag, ash, water, superplastic, coarse aggregate, fine aggregate, age. So 8 inputs, and based on that, we are trying to predict the strength. So that is the output. So it is a concrete strength prediction that we are trying to do. It's a regression problem, and it will be a multiple linear regression problem. It's very interesting. So a couple of things that we have done in this exercise, you can see. So first things first, I've actually done a small pair plot of my data. So pair plot is a wonderful visualization technique which helps us to visualize the correlations between the different variables in terms of scatter plots. And along the diagonals, we are also able to see the distribution plots. So if you see the diagonals here, the diagonals are very clearly demonstrating the distribution plot of my data. So here you can see the distribution of cement, distribution of slag, distribution of ash, water, superplastic. So this is very similar to what I talked about a while back with respect to the histograms. So you can see the smooth histogram for all these variables. So you can clearly see the skewness. You can clearly see that some of the features are very symmetric, whereas some of the features like strength are a little bit right skewed. Okay, so this is a good scope that we get to now apply some pre-processing techniques, some transformation-based pre-processing techniques that we can apply now. Okay, now this is the correlation part that we are calculating. So we can do data.core, and this is how we can calculate the correlations. So when I do data.core, what happens is we can compute the correlation between the different set of numerical variables, right? So we have got 8 features, and we can compute the pairwise correlation between every single pair of feature. So this is how we can compute the correlation. So we can basically compute the correlation between every single set of feature. Okay, so the correlations we can compute, and we can also visualize the whole thing in the form of a heat map. So we can create a heat map, and we can visualize the whole thing in the form of a heat map. So that's the visualization that we are doing. And if you see right now, what are the key takeaways from this particular heat map correlation visualization? So we can clearly see that strength is the output. Strength is what we are trying to predict. And we can clearly see that cement is the strongest predictor of strength. So out of all the features, we can see that cement is the strongest predictor of strength. So cement is the strongest predictor of strength. That's the inference we are able to make out. Okay, so out of all the features, cement has the strongest correlation, 0.5, followed by superplastic, followed by age. Another very interesting observation that you're able to make out here is that none of the features are exhibiting a very strong relationship. Unlike the data set on advertising, you can see here, all the features are having moderate to weak correlation. None of the features are demonstrating a very strong correlation. So even the cement feature, if you see, is having only 0.5 correlation, which is very low. That means if you take individual features here, like what we were doing in the advertising data set, here if you take individual features, if you try to build a model only with cement, if you try to build a model only with plastic, super plastic, coarse aggregate and all that, you will get a very low R squared. The R squared of the model will turn out to be very, very low. So that is another very important concept to be kept in mind. Next up, we are just building the regression model. This is something everybody has done. You have split your data X and Y. And this is the code that we have used, data.drop. We are dropping the strength column, and everything else is basically part of my X, and strength is part of my Y. After that, linear regression, model.fit X train Y train, and you're finding out the coefficients and intercepts of the model, and this is the R squared scores. And you can clearly see that the iteration 1 linear regression model that we are getting is giving us around 60% of training accuracy and around 60% of testing accuracy. And as I said, I'm using the term accuracy and R squared interchangeably. So we can say that yes, R squared of the model is 60%, which is kind of an underfit model. So to start with, we are getting a highly underfit model. The R squared of training and testing both are very, very low. And there is scope to make it better. We can build a better quality model. What is the reason why the R2 scores are very low right now? The reason is because the patterns in my data are non-linear. If you look at the real world data patterns, the patterns in the data are extremely non-linear. Okay, so the patterns in the data are highly non-linear. The overall patterns in the data are highly non-linear. And what we are trying to do is we are trying to build a linear model on this data. So despite the data patterns being highly non-linear, we are trying to build a linear uh, model on this particular data. And hence it is coming out to have a very low accuracy overall. That's the inference. We talked about cross-validation yesterday, and cross-validation is the idea where we don't want to judge the model based on a single test accuracy. Rather, we want to compute 10 different accuracies and take the average. That is the whole idea of cross-validation. So, instead of relying on a single accuracy score to evaluate the model quality, we compute 10 different accuracies and evaluate the average cross-validation accuracy. So that's what we do. We get 10 different accuracies and take the average score. That's what we do as part of cross-validation. The second idea that I wanted to clarify here is you can see that if you remember, we saw that in the original distribution plot, a lot of features had a substantial amount of skewness. When we looked at that distribution plot, we saw that there were some features which were right skewed and there were some features which were left skewed. And we also discussed a little while earlier in the discussion that skewness is a bad thing. Whenever your data is skewed, in this case, we have certain features, right? So whenever we have skewed features, the model we end up building will also be skewed. So this is the real problem that we are facing right now. So if we are working with skewed features, which we have in this case, and if you are using this as part of supervised learning, the model will also be highly skewed. And that's the exact problem that we are facing right now. We are dealing with a highly skewed model here. Okay. How do we correct the skewness? What is the way to resolve the skewness? How do we mitigate the skew? How do we reduce the skewness in the data? We can use something called a power transformation. We talked about this discussion. We discussed about this, that where if we have skewed data, if we have right skewed data or left skewed data, then the supervised learning models will end up being biased. Okay, if you have outliers in the data, then the model will not learn those outlier patterns that well. It will learn the other patterns very well, but especially for cases where some values are very high, some values are very low. Like we took the example of salary. Salary is a right skew distribution. So if you have a right skew distribution kind of data, then if there are very high salary values, there are only few people in the company that make high salaries, right? So if you're building a supervised learning model on that data, then the model will not learn those patterns well because there are not enough examples to learn from. Okay, so maybe somebody in the 3 to 5 lakhs bucket, there are a lot of employees in that bucket. So the model has enough examples to learn from. But especially somebody in the plus 20 lakh or the plus 50 lakh bucket, the model will struggle because there are not enough examples to learn from. And how do we correct it? We use something called power transformer to reduce the skewness. We can make the distributions more symmetric and more normal. In case you are wondering what is going on behind the scenes, mathematically, power transform uses something called a Box-Cox transform. We use something called EO-Johnson transformations. And these are all different types of mathematical transformation techniques. These are all part of data pre-processing. So we take the original data and we try to apply different types of mathematical transforms like log transform, square transform, exponential transform, all of these kinds of numerical transforms we try to apply on our data to make them less skewed and more symmetric. Next up, we are going and applying the gradient boosting, which again, most of you have done. And you can clearly see before that, as you can see, with a baseline linear regression model, we were getting 60%, which all of you reported. And moment I apply power transformer and do linear regression, you see this 80%. I think this part, some of you did not do, but this is the improvement I wanted to also highlight, that the moment you correct the skewness in your data, the moment you reduce the skewness in your data, so after pre-processing, when you build the same linear regression model on the same data, see how the scores have become better. So we are getting a more robust model and a more accurate model after we apply power transformation. Okay, and this is the comparative understanding I was clarifying yesterday. So I was telling that, okay, whenever you evaluate a model, it's always on a comparative scale. So iteration one, what were the training and testing scores you were getting? And iteration two, how did the model improve? So did the training accuracy become better? Did the testing accuracy become better? So do we have a better model compared to what we had before? So that is how we evaluate these models. Okay. And this is with gradient boosting. Gradient boosting regressor is the other algorithm you're using. And with the gradient boosting regressor, you're getting again, a higher training and a higher testing accuracy. So the training score is around 94.8%, and the testing score is around 91.08%. So these are the two scores that we are getting right now. So we have a model whose training accuracy is 94.8% and whose testing accuracy is 91.08%. So these are the two different accuracy scores that we are getting right now. As you can clearly see, it's a better model. And one of the other key ideas that we talked about in the prior discussion was N estimators. And this is, again, a bit of a technical topic, but at a very high level, N estimators is a kind of a hyperparameter. It's a tuning knob. So every machine learning algorithm will have these kinds of tuning knobs. And you can actually find out what is the optimal value of N estimators to build a good quality model. Okay, so here we are taking N estimators equal to 100, but you can try different values of N estimators. And when you try different values of N estimators, you will see very clearly that the scores will vary a lot. So for example, if you take N estimators equal to 1, the training and the cross-validation scores. Cross-validation is nothing but a testing score. It's an average testing score. So the training and testing scores both will be low. So we saw that yesterday briefly. So if you keep a very low value for N estimators, the model will be highly underfit. And as you keep increasing the value of N estimators, the model will become more and more good fit. So if you have a higher value of N estimators, what will happen is the model will become more and more good fit. So that is the inference that we can get out of it. Okay, so for a smaller value of N estimators, we have a highly underfit model, and as N estimators keeps increasing, we have a more and more good fit model. So that's the inference we can get out of this. We have a more good fit model as we increase the estimators, and we are trying to find out somewhere in between, somewhere here. This is the vicinity where we are trying to find the good fit zone. The good fit zone is that zone where we have the highest test scores, we have the highest validation scores. Okay, because remember, beyond the point, if you continue increasing your N estimators, what will happen? You will reach overfitting. You will reach the overfitting zone where the training will continue to go up, but the testing will continue coming down. You'll reach overfitting. So you're trying to reach the zone where you get the highest validation scores. That is the good fit zone that you're trying to reach. This was a concrete data set. Then we looked at this very interesting New York City Kaggle competition. It was a very interesting competition. And what I'll do is we'll try to go over some of the ideas that are present in this particular problem statement. And it's a very real world use case where the different cab aggregators that we have, like Uber, Lyft, if you're in places like Singapore, Malaysia, you will use something called Grab. If you're in, let's say, other parts of the world, you have other applications that are there, right? So the idea is, if you're in India, we have Ola, Uber, obviously. So here, if you see, based on the different attributes of the ride, we are trying to predict what is the price of the ride. Again, it's a very real world machine learning regression problem that we are trying to solve. And if you look at the data set, every row corresponds to a particular ride. So we have the fare amount. What is the fare for the ride? The pickup date, the pickup latitude, longitude, the drop off latitude, longitude, and the passenger count. So this is my data set. You can ignore the key. The key column is an identity kind of column, so you can ignore that. But everything else apart from that are part of my features, X's. Okay. And what is the Y? The output is fare amount. Okay, so that is the X and the Y combination. So whenever you're framing, whenever you're trying to solve any regression problem, the initial phase is very important when you're trying to frame the problem. You need to be very clear what is your X and what is your Y. So this is my X. So whenever a person is booking the ride, they will enter all these parameters, right? Isn't it? So when you're opening up the application, you have a pickup time. Latitude, longitude is where your source location is, where you're starting from. Drop off is where you want to go. You will enter these parameters. You will enter how many people you want to travel with. Like, these are also important. Like if you're going to, like in certain applications, they ask you to enter how many passengers will travel. So depending on that, the pricing will also be adjusted. Okay, in US and all, this is very common. You have to enter the passenger count also. So based on these features, the model will predict what is the fare count. So the fare count is what we want to effectively predict. Okay. Now, this is again a standard, a very simple problem. So what is the key takeaway from this exercise? The key takeaway is we are trying to learn a lot of different types of feature engineering techniques, right? We are using a slightly different technical term right now, feature engineering. This is actually a very good use case for feature engineering. So feature engineering is the idea where we try to use a set of features. Okay, it is the idea where we try to use a set of features And based on that, we try to predict, we try to, kind of generate new features. So based on a certain initial set of features, we are trying to create new features. That is what we do as part of feature engineering. And why is it important? Why is it important particularly for this exercise? Because if you look at it, friends, if you look at the initial set of features we have, the initial set of features are not good. These are not good quality features. I mean, if you see latitude, longitude is not a good quality feature. This is not a good predictor of fare. If I want to predict the fare of a ride, latitude, longitude are numerical variables, right? These are useless variables. This is not a good predictor of fare. This is the same conversation I was having a while back. I told you that, okay, identity columns are bad features. They don't have any predictive information about the output. So similarly, latitude, longitude per se are bad quality features. What will be interesting to get from here? Maybe from latitude, longitude, I want to find out the place, the location of the ride. So if you're booking a ride in Bangalore, you want to travel from HSR layout to Koramangala, that is what is important. We want to look at the localities because the pricing will be dependent on the localities. Okay, so right now, let's say the heavy rains are happening, and if you're booking a ride from place A to place B, these kinds of models are getting used. The numbers are not important, like -73, +40 is not important. What is important is, can I map this latitude, longitude, and can I narrow down and say, hey, this, this is HSR layout. So the passenger is booking a ride from HSR to Koramangala. These are the features of the ride. You will one-hot encode these features, and now you try to predict the fare. That's the thing. Okay, so we'll go over that, but we'll see all those techniques right now. And the very, very interesting part of the exercises, we will see what are the different types of feature engineering things that we can go back and do here, right? So let's see. So first iteration one, what we do is we build a baseline model with the raw features. This is again a very, very common approach that we follow. So whenever we face with a difficult problem, there are a lot of things that we can potentially do. But one of the very first things that we should try to do is we should always try to build a baseline model. Okay, so this is one of the first things that we should try to do. We should always try to go and build a baseline model. So take the data as it is and try to build a baseline model with the raw features. So that's the first and foremost thing that we will try to do. So we'll try to take the data as it is, and based on that, we will try to build a baseline model. So build a baseline model using the raw features. So take the X and Y and build a baseline model. So we are getting something like 73%. So 73% is the R squared we are getting for the baseline model. So can we do better than this? Okay, because I told you, machine learning is a process where you're constantly trying to become better. It's a very exploratory process. We never know what will work, what will not work. So we are constantly going to try out different techniques now. So we'll try to add some features, remove some outliers. We'll try out different models, and we'll see which model is giving us the best performance. So this is kind of a very exploratory way how we will, approach this particular thing here. Okay, so now what we are doing is now we are removing outliers because there are a lot of outliers in the data. If you see fair amount, if we see the distribution of our data, we'll see that most of the fares are around $0 to $20 because most of the rides are normal rides. So the fares are all between $0 to $50. Most of the fares are here, and very interesting. There are some fares which are negative, and also there are some fares which are $1,200. Like, this is very hard to believe. Like fare of a cab ride is $1,200, and that too this is within NYC. So within NYC, if you're traveling from some place to another place, like $1,200 is like that's a lot of money. That's huge. That's huge. I mean, it's hard to believe that within NYC, if you're traveling, the fare can be this high. So most likely this could be some outstation ride, or maybe the GPS coordinates were not picked up correctly, or there were some errors in the application, and we will want to remove this kind of data. Because remember, if you have outliers, and if those outliers do not make sense, right, as I told you, like some extreme values with really high fare and negative fares, like maybe they are potential outliers. We don't know. We don't know. They are potential outliers. And if you look at this in detail, if you look at the another thing, if you look at the latitude, longitude of the bookings, you will see very interesting. Most of the rides happened here, but there are some outliers. This is the latitude, longitude of New York City, right? But you will see that there are some rides. There are some rides that happened beyond these coordinates. So there were some rides that were booked away from New York City. So most likely there were some GPS errors. Oftentimes it happens, like, because GPS depends on your mobile phone, right? So it can happen that you're booking a cab, but the GPS is not picked up correctly. So maybe the source is taken to be something else and the destination is taken to be something else. It's very normal, very common. Sometimes it might happen. It might happen that the GPS coordinates are not picked up correctly, right? So now we try to build another baseline model after removing the outliers. So now you remove the outliers and you try to build another baseline model. And these are the scores you're getting, 76%. So can you see the small improvement that we got? So iteration 1, we got 73%. Okay, so this was the baseline model that we built initially. We got 73% accuracy. And iteration 2, we removed the outliers and we built a model. And now we are getting 76% accuracy. Okay, so when we remove the outliers and now we build another model, and now we are getting 76% accuracy. So that is the R squared we are getting now. Small improvement. See how small improvements we are making. Iteration number 3, experiment number 3. Now what we will try to do, we have a date time feature, friends. Okay, remember we have a date time feature. So date time is not a useful column. Okay, so if you want to predict the fare of a ride, let me take you back to the original data. If you want to predict your fare, this is not a good predictor of fare. So if I just try to take this as X and try to predict this Y, you will not see a good relationship because this is a date time format, right? This is useless. You will not find any correlation. So you have to convert this data. So from the date time column, we can try to find out temporal features. What are temporal features? We can try to find out features like, hey, what is the hour of the ride? Okay, what is the time of the ride? Something of that sort. So these are the kind of features we can try to decipher. Okay, so from the original date time feature, we can try to extract temporal features: year, month, day, hour, day of week. Now the whole idea is once you end up creating these features, you can see we have created all these 4-5 features here. Now we can remove the date time feature and say that, hey, keeping every other factor constant, this is a good predictor of the output. So, I mean, you can say the day of the week is a good predictor of the fare, which is expected, right? See, Monday to Friday, these are the weekdays, right? So typically the fares will be high. Given every other factor is constant, even if you look at rush hour 9 o'clock traffic, Monday to Friday, 9 o'clock bookings, the fares will be high. Saturday, Sunday, 9 o'clock bookings, the fares will be low. So keeping every other factor constant, the day of the week is a good predictor of fare. If you tell me what day of the week it is, I can predict that whether the fare will be high or low. This is a good feature. The hour of the day is again a good predictor of the output. If you look at the hour of the day, typically again, it's very obvious, right? So if you look at anywhere, I think the rush hour usually starts from 8 o'clock. 8 o'clock very easily is the rush hour. So 8 o'clock to night 8. Morning 8 to evening 8 is rush hour. Right? Generally, it can be different for different parts of the world. I mean, if you look at India, 8 to 8 is very normal. If you look at Middle East, then I think it's work starts very early here. It's 6 o'clock, so 6 to afternoon is very normal. So peak hours are different, but then the idea is that 8 to 8 is like keep every other factor constant. The hour is a good predictor of fare. Okay, if you're trying to book a cab at 2 o'clock at night, the fares will be low. Even if you're booking a ride from HSR to Bangalore airport, you will see that if you're booking at night, middle of the night, the fares will be very, very low generally. Okay, so now moving on with these features, we are building the model and we see 77.5% R squared. See how we are making small incremental improvements in the overall performance. This is the way how we actually build machine learning models in the real world. Okay, because our data will be very difficult. So we will always experiment. We will never know what will really work. We will try out, we will try adding features, try removing outliers, try different permutation combinations, and try to improve the model. That's why we say that in machine learning projects, typically getting a POC ready is very easy. It's very easy to take some data, take some sample data, use Python, use the sklearn frameworks. You can very easily create a proof of concept. That is very easy. There's nothing. In fact, after we complete these discussions, everybody should be able to have a working proof of concept in a matter of like what hours. Shouldn't take much time. Okay, with all the generated tools that we have. But what will take time is doing this. This is the part that will take time, and oftentimes this is the part that your tools will not help you. You need to brainstorm. You need to figure out, okay, based on my domain, what I think are important. See, like for example, adding trip distance as a feature. Now remember I told you latitude, longitude are the original columns I had, but they are useless. But from latitude, longitude, what I can do, I can now try to add another feature called distance. Distance will be a very good feature. I mean, keeping every other factor constant, distance is a very good predictor of the fare. So it's obvious, right? If you travel more distance, you will pay more fare. If you travel less distance, you will pay less fare. It's very obvious. And the moment I include that, my R squared has shot up 83%. So see the process we are following right now. So we are using domain knowledge. We are making a hypothesis that, hey, I think this will work. I think this will work. You're using your domain knowledge. You think that, okay, based on the CAB data set, I think that distance is a good predictor of fare. You have a hypothesis. Then you build a model and you try to test the hypothesis. That's the way how we are going about it. Okay, so this is the general process we will follow. So you have a hypothesis, you think this is a good predictor of fare, and then you are actually using you're actually building a model to test your hypothesis. And indeed, you're getting 83% accuracy. So indeed, our hypothesis is true. So it's a good quality feature. So we have made an incremental improvement in the overall model quality. So the same way we are trying the other features, we are adding a feature for airport trips. You can see that here we have added a set of 6 features for airport pickup and drops. So there are 3 airports in and around the vicinity of NYC, New York City. So John F. Kennedy International Airport. Is it a pickup ride from JFK? Is it a drop-off ride to JFK? Is it a pickup ride from Newark Airport? Is it a drop-off ride to Newark Airport? Newark, Newark, Newark. And is it a pickup ride from LaGuardia, or is it a drop-off ride to LaGuardia? And again, if you think about it, this is important because, again, keeping every other factor constant, if I know it is an airport ride, the fares will be high. And if I know it is not an airport ride, the fares will be low. So knowing whether it is an airport ride or not an airport ride is also a very, very important characteristic. So we are using that and building the model. It's a very, very small improvement that we are getting. 83.1% accuracy we are getting right now. So this is the information that we are getting right now. Next up, we are trying with long and short trips as a feature. So we are adding a calculated feature for long and short trips. So we are looking at the distance and trying to classify whether it is a long trip or whether it is not a long trip. So this is the classification that we are trying to do. Okay, so based on the features, is it a long trip? Yes. Is it not a long trip? No. So by adding this once again, we have made a small incremental improvement in the quality of the model. So this is all the different techniques we are trying out. And by doing all of that, by fine tuning, by adjusting the hyperparameters, we have finally got a model which is 86.5% accuracy or R squared. Okay, so this is the key takeaway from the exercise, where it's a wonderful application of feature engineering, where we start off with a data set with absolute raw features like latitude, longitude, time, like how the real world data will look like, and how from that completely raw data set we have managed to apply different types of domain-based feature engineering techniques, and we are able to build a much better quality model. We've created better quality features. We created features like distance and all that. And by doing that, we have managed to create a much better quality model. So which is giving us a score close to 86.5%. Okay, so all of you can see that. So this is the inference of the New York City data set. We can extend this conversation, to multiple things. We can also extend this to time prediction. Oftentimes, the taxi rides will also tell you how much time it takes to reach the destination. So even that could be thought of as a regression problem. But more often than not, what they do is they use Google APIs. Like if you look at Uber, Uber uses the APIs from Google. So they will use Google Maps. And again, it might be different from in different parts of the world, but they might be using Google APIs where moment you plug in the source, moment you plug in the destination, the time prediction will happen from Google. But even Google is doing regression behind the scenes, right? Because even if you see Google Maps, how they are, like if you enter, I want to travel from point A to point B, there is some algorithm, there is some predictive algorithm that is being used to estimate how much time it will take to reach from point A to point B. That is also an excellent regression problem, but it might not be directly done by Uber. So Uber is simply using the Google interface to compute the predicted time. Okay, but they are related. So the exercise that we saw to predict the fare, it is very similar to the exercise for predicting the time. So they're both very similar ideas. Okay, the next case study was on Mercedes. This is also a very, very interesting case study. And to understand this case study, I want to discuss another very general concept. I want to discuss a very general concept with all of you, how we go about it. So we'll talk about this in more detail once we cover up the clustering parts in our discussion. But before we discuss the Mercedes case study, I wanted to cover up this very, very interesting concept from a, So let's say we have a data set and we are trying to do a housing price prediction. Okay, we are trying to do a housing price predictions. We have the size of the house, and based on that, we want to predict what is the price of the house. Okay, so the objective is we want to do a kind of a housing price prediction where based on the size of the house and different other features of the house, we want to predict what is the price of the house. This is a price prediction that we are trying to do. Okay, this is how the distribution of my data looks like right now. Everybody can see the screen. So you can see size along the x-axis and price along the y-axis. Then you all know the real estate market. There are different types of properties, friends. We have got 1 BHK, 2 BHK, penthouses, duplexes, apartments. And obviously, you can understand that the relationship, the dynamics around the pricing will be very different for different types of houses. If you look at 1 BHK, the dynamics are different. If you look at 2 BHK, the dynamics are different. And if you look at different categories of housing, if you look at different categories of housing, the dynamics will be very different. That is important to keep in mind. Now, we can follow the same approach. Whatever we talked about, we can absolutely solve this in the same way. So we can collect a whole lot of historical data, uh, different types of houses that we have. Like we can look at a whole host of houses from our repository. We know the size, we know the price, and we can absolutely build a regression model, exactly like the way how we discussed so far. We can build a regression model on this data, no problem. Now, the issue is that there are so many different types of houses that if you try to build one single model on the whole data, that model will not be able to give you very good results. Look at the patterns right now. Look at the size versus price dynamics here. So there are a lot of variations you can see, right? Especially if you see the lower end of the spectrum for 1 BHK and smaller houses, it's more of a linear pattern. If you look at the middle segment, 2 BHKs, you see a more of a polynomial pattern. And if you see the segment somewhere in the upper end, the penthouses and 3 apartments, you see a more of a logarithmic pattern. So the patterns are different, right? And on this entire data, if I try to build a single model, let's say if I try to do a single linear regression, it will never work. And this is also applicable for many real world use cases. In the real world, whenever you have some data and you're trying to build a model, going back to the fundamental ideas of supervised learning that we discussed, if you take the entire data and if you try to build a single model on the whole data, they will never work. So you cannot build one single model on the entire data. Okay, so you cannot build one single model on the entire data. That will never work. So how do you go about it? What do you do? What do you do? How do you work it out? So what you need to do now is you need to go and take the whole data, do clustering, divide the data into multiple different groups or clusters. And this is an approach we will learn in the next discussion that is planned for tomorrow. We'll see clustering techniques, K-means clustering, how it is done. But this is the big picture, end-to-end understanding I'm trying to give you, how it's actually done. So you take the entire data and first you do clustering. You try to identify how many groups of data do we have. So from the entire houses data that are there, can we try to identify the different groups and clusters of data? Let's identify that first. What are the different groups and clusters of data we see? So we have small houses, we have medium houses, we have large houses. This is how the distribution looks like for each and every individual category of house. You can see small houses can be represented somewhat like this. Medium houses can be represented somewhat like this. And large houses can be represented somewhat like this. We have basically broken it up. If you see that small houses are basically this part. That's small houses, that's medium houses, and that's large houses. So we've kind of separated it out. Now here I know it's very simplistic. So we only have a single dimension. So it's very easy to understand what's going on. But in a more real world scenario, we will have multiple features, multiple dimensions, and it won't be as easy to visually see. But the idea should be clear. We take the entire housing data and we try to understand what are the different groups and clusters of houses that we see. That's what we are trying to figure out. And once you understand the different groups and clusters of houses, now you can build separate regression models on each and every group and cluster of house. So you basically have three different data frames right now. You have a data frame separately for the small houses, you have a data frame separately for the medium houses, and you have a data frame separately for the large houses. So now you can look at the small houses and you can build a separate model only for the small houses. You can look at the medium houses and you can build a model separately for the medium houses. And you can look at the large houses and you can build a model separately for the large houses. So you can orient your data this way and you can build models separately for each and every individual group or cluster of house. The small houses build a separate model, medium houses build a separate model, and large houses build a separate model. So you have the individual models now, and this will be much more accurate. This approach will give you much more accurate results than if you had built a single model on the whole data. Okay, if you had taken the entire data here individually, the results would have been, you know, the results would not have been that accurate. Okay, so if you see, if we had taken the entire data here, if we had taken the entire data here and built a single model, we would not have got such an accurate result. But the moment we split our data into different groups, and on each and every group, we are building a separate model, we're getting more accurate results. See how we are able to fit the points a lot more accurately. Okay, so this is the general concept I want to keep in mind. Why are we talking about it? Why are we talking about it now? Why now? The reason is because we are going to be discussing the Mercedes greener manufacturing case study. It's a very, very interesting, very real world data set. So that was the whole objective. I wanted to, kind of show you, how the simple ideas of regression that we covered, how they are used in the real world, in real competition by real companies, and not like a concrete data set. It was a very academic exercise we did, but more like in the real world, how we can relate to it, like a Uber, like the taxi one, like the Mercedes one. So you can, relate to the core ideas better. Okay. So this is also a very, very interesting use case where we are trying to predict. We are trying to predict how much time it takes to test a car. Okay, so Mercedes cars are highly customized. So customers can literally customize every single aspect of the car that they want. Okay, so you can literally go to an application, a web app, and you can choose from the set of features, and you can order the car, whichever and howsoever set of features you want. You can customize the car in a very detailed manner. Now, the important thing is that car needs to be tested. Somebody needs to test the car, right? Many of the things are software oriented. So, even in the software, let's say you have a infotainment system, you have a destination navigation system, and you can decide what features you want, what features you don't want. So when the final car is delivered to you, some of those features will be turned off, but it has to be tested. Before Mercedes delivers the car to the customer, they have to exhaustively test the car to make sure all the features are working in tandem. And that is exactly where this use case is. Okay, so this is the use case we can see, but optimizing the speed of their testing systems for so many possible feature combinations is complex and time consuming, because customers can order different types of cars, right? So I mean, if there are so many different types of features that are technically possible, it is very difficult to manually test each of the combinations. So how can we use machine learning to predict how much time a car is going to take to test? So that's the whole idea. And these are different types of features that are there. So if I just quickly take you to the solution file, we've actually used a very similar approach here also. So we've grouped the data into different types of cars, and then we have built separate models for each and every type of car. So we followed a very, very similar approach to what we talked about just a while back, the clustering based approach. Okay, so here also, if you see, there are two notebooks. One is a pure play modeling based approach, and the second notebook is more of a simple exploration, an EDA based approach, where we are trying to explore the data a little bit more in detail. Okay, so I will just very quickly go over it. I will not take you through it in detail, but very quickly go over some of the core concepts. This is my data set. First of all, it's a very real world data set. You can see x0, x1, x2, x3, all the way up to x385. There are total 386 features in a car, and all these have been anonymized. We do not know the exact feature names, because this is again very confidential data, and Mercedes does not want to reveal the exact features of their cars. So each of these columns that you see, they correspond to different types of features in a Mercedes car. So maybe this is like a destination navigation system. Mercedes cars, they have some of the top end models, they have something called destination suggestion. So you can literally sit in the vehicle, you can turn on your car, and the model will look at the historical data and predict where you might want to go next. So it quite literally looks at the time of the day of the week, what time of the day it is, what was your past travel history. let's say today is a Monday and 9 o'clock I start the car. So the model knows that, hey, I'm going to office, or most likely I'll go to the office because that's what my history suggests. So this is that kind of a feature, let's say as an example. So we've anonymized it. And these values stand for, okay, these are the cases where the feature is not present, and this is the case where the feature is present. So that's how the data actually is like. So each of these are feature names. Imagine this is like another in audio feature. So in all these cases, the audio feature is not present. In all these cars, the audio feature is not present. In this car, the audio feature is present. So you have this is like a binary variable that we have right now. And based on all this, we are trying to predict the y. The y is the testing time. This is the testing time that we need to predict. It's a variable we have to predict. Now, very interesting. If I do a distribution plot on the y variable, you will see a histogram that looks somewhat like this. So we've talked about histograms already some time back, and we understand that histograms are able to show the distribution of my data. So the moment we do the distribution of the y variable, we see a histogram that looks somewhat like this. And if you try to analyze this a little deeply, you will see that the pattern looks somewhat like this. This is what the pattern looks like. So you basically end up seeing three broad distributions. Okay, so if you look at the y variable a little bit more in detail, you will broadly see three distributions. Okay, I repeat again, you will broadly see three distributions that are playing out. So these are the three distributions that you will see. Okay, so you'll observe that these are all the cars which are having the testing time. Y is the testing time, right? What is Y? Y is the amount of time it takes to test a car. Testing time. So you'll clearly see that. So you'll clearly see that there are a lot of cars which are having the testing time which is average to low. So most likely these are very simple variants of cars. So there are a lot of cars which have testing time which is average to low. There are a lot of cars which have testing times which are around this, and there are a lot of cars which are very high testing time. So very clearly, by looking at this data, we can understand that there are broadly three different groups or clusters of cars. So how many groups or clusters of cars do we see? We are broadly able to see three different groups or clusters of cars. That is the inference we are able to make right now. Okay, so we are able to see three different groups or clusters of cars. Okay, so we have got the cluster one type of cars which are having average to low testing time. We are having the cluster two type of cars which are having mid testing time. And we are having the cluster three type of cars which are having very high testing time. So we are able to kind of segregate cars and create different groups and clusters of cars based on their testing time. That is the inference we are able to make right now. Now, why is it important? Why is it important? Why is it important to do the segregation? Because when we try to eventually build a model, to predict testing time, remember the dynamics will be very different. The dynamics of these cars are very different. If you're looking at cars which are having testing time from 0 to 80, these are very basic cars. They don't have too many features, which is why they are taking very less time to test. These are very, very like low-end models, initial like base models we can call it, right? They don't have too many systems and there's not too much complexity interactions between the systems. So that's why testing these cars is a lot easier. And the models will be very different for these kinds of cars. If you want to build a prediction model, the prediction models for these cars will be very different. But if you talk about the top end cars and the absolute top end luxury cars that we have, like which are taking a lot of time to test, the features are very different. So some of the features present in those top end models are very different. Maybe some of them will have a lot of AI based features, a lot of self-driving, assisted driving features, ADAS, driver assistance systems features you will have, which the base models will not have. And testing those things will take a long time because safety standards are paramount, right? So before you send a car to the customer, you want to be absolutely sure that all these are working, all these systems are working fine. So the moment you're putting in those driver assistance systems, cruise control, lane assist, parking assist systems, automatic parking system, which Mercedes cars have, by the way, all the modern day cars, they have those kinds of basic AI assisted features. And the moment you incorporate those things, it's a very different breed of cars. The dynamics are very different, just like the houses example. So we need to build a different model. And I wanted to mention this because next time as we do the exercise, as we see more and more case studies, always try to think from the perspective of building multiple models. So in production also, companies will never have a single model. They will always have multiple models on that they will build on different groups and clusters of data. This is again a very, very important concept that I wanted to highlight. Rest of the part is very straightforward. So I'm going to stop from here and we'll move on. Okay. Yeah. So I've already uploaded this part. And now what we will do is we'll enter into the beautiful ideas of classification. So far we have basically understood about some of the foundational concepts of regression. And now from here, we'll try to understand what is classification. Now we already discussed classification. We already briefly discussed what is classification in the session yesterday. So we know that in regression, we are trying to predict a number. Whereas in classification, what is you are trying to predict a category. So we know that. We know what is classification. What we are doing now is we are trying to give you a slightly more pictorial understanding of classification. Okay, how do you think of classification a little bit more pictorial? See, even for regression, if you remember, I told you that in regression, the output is a number. We are always trying to predict a numeric output. Regression, we are always trying to predict a numerical output, a numeric output in regression. But we also discussed a visual approach yesterday. What is regression visually? We are trying to find what is the line or plane or mathematical surface. Okay, so what is the line or plane or mathematical surface that best separates the classes? I'm sorry, that best fits the points. Right? All of you remember that, right? So in regression, the theoretical definition was, yes, we are trying to predict a numerical output. The practical demonstration, the visual demonstration was like that in regression, we are trying to find the line or plane or surface. I say surface because it doesn't always have to be a line. It can be non-linear also, right? So we are trying to find what is the line or plane or surface that best fits the points. That's regression. Same way we try to understand classification now. Okay. In classification, we are trying to find out what is the line or plane or surface that best separates the classes. Okay, so what is the line or plane or mathematical surface that best separates the classes? That's the way how we understand the core ideas of classification. Okay, so you have some data and you're trying to find out what is the line or plane or mathematical surface that best separates the two classes. That's the way how we understand the core ideas of classification. Let's take the same example. Let's take a beautiful example here. So we have a use case of a self-driving car. Very, very simple analogy of a self-driving car we are taking here in this example. So we have the different attributes of the road conditions, which are steepness and bumpiness. So steepness and bumpiness are giving us the different attributes of the road conditions, how steep is the road and how bumpy is the road. Okay, so we are looking at the different attributes of the road conditions, how steep is the road, how bumpy is the road. And based on the different attributes of the road conditions, we are trying to predict the speed of the car. So based on the steepness of the road and the bumpiness of the road, we are trying to predict, will the car go slow or will the car go fast? Okay, so I repeat again, based on the steepness of the road and the bumpiness of the road, we are trying to predict, will the car go slow or will the car go fast? So once again, we are taking the entire historical data. So this is a whole bunch of historical data that we are considering. And you have all these different patterns that are playing out, you can see. So you're monitoring the car and you're training the car, because we know that we have to, in order to build a supervised learning model, we have to train the system over different data points, over different iterations. That's exactly what we are doing. So we are considering different instances. So you can see that when the road is less steep and less bumpy, the car is going very fast. Lots of greens here. Okay, so you can see every dot corresponds to one instance. So whenever the road is very steep and very less steep, it's not very steep and not very bumpy. So steepness value is low and bumpiness value is low. So whenever you are in this zone, the car is going fast, greens. And whenever the road is very steep and very bumpy, or either steep or bumpy, the car is going slow. That's the way how you train the car, isn't it? So it's like it's like you're teaching a kid how to drive. So when you're teaching a kid how to drive, you will first drive the car yourself, and only then the kid will learn. Right? So this is how exactly we are collecting our data samples. Right? In case some of you in this, in the audience are wondering that, hey, how are we getting this data? How are we collecting these data samples? This is exactly how we are doing that. So in order to teach the kid, we have to drive the car ourselves. And this is exactly how we will drive the car. If the road is not steep and not bumpy, we will go very fast. If it is steep and bumpy, we will go slow. That's it. That's how our data is right now. That's how we get the XY combinations. And once we have the input output combinations, you can see this is the categorical output variable. We will use some algorithm and we will build a model. Now, what is the model? The model will be an equation. It's a linear equation or a nonlinear equation. And we also call it a decision boundary or a decision surface. Okay, so in the world of classification, that model that you end up building, that model is also called a decision boundary, or it is also called a decision surface. That is what the model refers to here. So we take the data, we use some algorithm, and we build a model. And that model is a decision boundary or a decision surface. So this is what you end up learning in the process. So when you do model.fit, this is the boundary that you end up learning. This is the result of model.fit. You end up learning the decision boundary. That means you are able to separate the reds and the greens in the most optimal way. This is the line of best separation. Yesterday, regression was line of best fit. We are trying to find the line that best fits the points. In classification, you are trying to find out what is the line or plane or surface that best separates the classes. You are trying to find out the best separation. What is the line that best separates the reds from the greens? You're trying to find the separation here. And once you get the model, once you have the final model or the decision boundary, once you have this thing, next time I give you a new data point, let's say you have a new instance of a car, and for the new instance of the car, you have steepness is 0.3 and bumpiness is 0.4. So now you have the new instance of the car, and you want to predict what is the speed of the car. So you will see that, hey, I think 0.3, 0.4 is on this side of the line, so the model will predict fast. That's the way how the fit and predict will happen for classification. So very important. We talked about the pictorial understanding of classification here. So yes, we are trying to predict a category, but how do we think through it? How do we think through a classification problem? What is it? What is actually going on behind the scenes in classification? So in classification, we are trying to find the line or plane or surface. What is the line or plane or mathematical surface that best separates the classes? We are trying to separate the reds from the greens, right? We've got lots of reds, we've got lots of greens. So we are trying to find out what is the line or plane or mathematical surface that best separates the classes. That's what you're trying to do in classification. You're trying to find the surface of best separation. Whereas in regression, if you remember, we are trying to do a best fit. We are trying to find what is the surface that best fits the points. That's what we are trying to do in regression. Okay, I think it's best understood. It's the best way to learn anything is through lots of examples, lots of pictures, and that's what I also believe in. So let me show you this beautiful example of regression and classification pictorially. I showed you one example yesterday, and I'm going to go to Google and show you a couple of images. This is the image I was trying to show you. Okay, look at this. Yeah, it's a bit coming a little hazy, but you get the idea. I think you get the idea what I'm trying to relate to. Yeah, let me open it up. Okay, I think we get the understanding here. Let me just open up from this image itself. We are able to follow. I think this is good enough to understand. So you can see in the regression part, what are we doing? We are able to like this is the part we already saw in the conversation yesterday. I think we understand that in regression we are trying to find the line or plane or surface that best that best fits the points. That's what we are doing in regression. So what is the line or plane or surface that best fits the point? So overfitting will look somewhat like this. Okay, underfitting will look somewhat like this. Good fit will look somewhat like this. Okay, so this is how we can understand the ideas with respect to regression. Now, if you go to classification, the idea that I just now talked about, if you go to classification, uh, underfitting will be like this. You've got lots of oranges, lots of blues. Underfitting is where you're not able to learn the relationship at all. So you're trying to ultimately find the separation between the classes, right? You're trying to find the separation between the orange and the blue. You're not able to find a separation. So, you're not able to separate the orange and the blue in the training itself. So it's a very, very bad model. Overfitting, you're doing too well. On the training data, you get a perfect separation. That's overfitting. Too complex, too many twists and turns, but you do a perfect job in the training data. Right fit is somewhat like this, more or less. Okay, okay. That's the way to pictorially understand regression and classification. So regression is always best fit. You're trying to best fit the points. Classification is best separation. You're trying to best separate the classes. Okay. Now what we will do is, given this idea, but everything else remains exactly the same. So many of the core ideas that we covered yesterday, train, test, plate, the process of building a machine learning model, uh, some of the correlation concepts, histogram, power transform, the ideas of encoding that we talked about today, like one-hot encoding, label encoding, how you use pipelines, overfitting, underfitting, the process of using cross-validation, all these core ideas remain exactly the same. Okay, so we look at our very first exercise of classification problem. We'll take a very simple data set to start with, and you will realize you'll actually realize that it is so similar. The code is quite literally exactly the same. There's hardly any difference you will find. The only difference is in the kind of algorithms that are used. Okay, so for regression yesterday, we used something called linear regression. And for classification, we will use something called logistic regression. Okay, and there are other kinds of classification algorithms that we will discuss. So first of all, let us understand our data set, what kind of data set we have. And classification will be a very long discussion because there are a lot of different types of use cases that we will talk about. So first, we will start with some academic examples just to build the foundations in terms of what is classification. And as we are able to understand the different concepts and the different ideas of classification, so from there we'll enter into some very, very real world use cases in terms of how classification is done. Okay, so this is the data set that we are taking up right now. We're looking at the different features of a particular person. And based on the different features of a person, we are trying to predict whether a person is diabetic or not. Okay, so you can see predict the onset of diabetes based on diagnostic measures. Okay, and also we are seeing a rapid amount of progress happening, especially in this field of in this specific field. We are seeing a lot of companies and especially a lot of healthcare companies, a lot of health startups are uh, jumping on the bandwagon where they are looking at your health history, they're looking at your diagnostic test results, and based on all the different parameters, these companies are trying to predict. Okay, so based on all the different parameters, these companies are effectively are trying to predict whether you will have a particular disease or not. Okay, so it's a very real use case that we are talking about. Okay, so it could be diabetes, it could be cancer, it could be other kinds of diseases. Okay, a lot of these kinds of models were used during COVID, right? So how you can take preventive action, you can identify based on certain types of symptoms whether a person is likely to have COVID or not. So again, if you think about it, they're all classification problems. So based on a set of features, based on a set of attributes, you're trying to predict whether a person has a medical condition or a person does not have a medical condition. Okay, so that's the thing that we are trying to solve. These are some of the features we have. Do not need to memorize all this in detail, but just to get an idea so that we relate to, we understand what we are trying to solve here. So every row stands for a person, and we have the different features of the person. So you can see that it stands for the number of pregnancies, the amount of plasma glucose in the bloodstream, the blood pressure of the person, the skin thickness, the insulin level, the body mass index, the body mass index, the diabetes pedigree function, and the age. So these are the 8 different features of a person. And based on the 8 different features of the person, we are trying to predict what is the class. Okay, so I repeat again, based on the 8 different features of the person, we are trying to predict what is the class. Okay, if the class is 1, that means the person has diabetes, and if the class is 0, the person does not have diabetes. Okay, class 1 means person has diabetes, and class equal to 0 means person does not have diabetes. That's the problem that we are trying to solve here overall. Okay, so now let's move on. Let's come to the actual solutioning. Okay, this is the thing. All of you can see. So initial part is very straightforward. We are loading the libraries and we are using. So in many times in my code, I just want to clarify one thing. Many times in my code, you will see this command called drive.mount g drive. You don't need this. I already clarified this yesterday. You do not need this. In case you come across this particular syntax, you can safely ignore it. All that this will do is it will load my Google Drive on my collab. Okay, if you want to see, I'll run this for you for a minute. I'll show you what I mean to say. So if I run this code, you will see after a while when I mount it, this G drive will be available in my collab, in my working directory in collab. This is what will happen. So, but you don't have to do it, okay? It will ask me to, I have to give it permissions to, connect my notebook to my Google Drive. I'll say connect to Google Drive and I have to sign into my account now. Continue. You have to give access to all these 9 services, which I already did before. So, but if you get some check boxes, just make sure to check everything. And once you do that, this drive will be available in my working directory. And I should be able to access all the files from my Google Drive. That is the concept. So no such directory because that directory does not exist right now, but that's okay. That's not that important right now. But you can see, I think, yeah, Outlook.com is the same folder, but I think this is the different path. I can modify the path, and if I modify the path right, it'll be fine. If you want to know how to do it, I can show you. So this is my, again, if you just refresh, you will see my uh, you know so if you see in the content, so I have mounted my G drive, and if you just go back to the previous directory, you will see that my G drive is mounted. Can you see? This is my G drive. Okay, so if I expand this folder, G drive, my drive, I should be able to access all the contents of my G drive, my drive. Okay, and I can copy the path, and that will work fine. And I think here it is giving an error because I think the right thing is not set. So I can just go and make sure I type in the right thing. Gen AI training main. I can also copy path and show you that way. But let me show you this way. So AI space Gen AI training main. So AI space Gen AI. Gen is capital or small. Let me just see. Yeah, Gen AI training main. I'm just doing it in a very manual way, but you don't have to. Okay, so that's why I say it. I mean, you can absolutely do copy path and do it. And this is general machine learning training. This is fine. General machine learning training, and then diabetes detection case study. This is also fine. Diabetes detection case study and Pima Indian diabetes data. Okay, I think this looks okay. And if you see when I run this code now, it will be fine. So it's already mounted. Now it's taking the data from my G drive, my drive, and inside that I've got all these folders. I'm not showing that right now. This is my Google Drive space. I'm not showing it directly, but you can see that this is all present in my Google Drive right now. You all have the folders here. But you don't have to do it this way. If you're trying to run this at your end, you can simply upload the file and you can work it out. I already showed you a very easy way to work it out. Okay, if you think all this is too complex, then you can just directly upload the file. Just directly upload the file. You have an upload button, upload the file, and you can work with it, right? But this is also very helpful in a very practical situation. This is also very helpful in scenarios where you've got very big files. Maybe not in this session, but especially once you go to advanced computer vision, once you go to generative AI, you'll be working with very, very big data, let's say of the order of magnitude of hundreds of GBs worth of videos and audio data. So in that kind of a scenario, it is very difficult to download and upload your data. Even if you try to upload your data into your session storage, it will take like hours to do it. But if you already have something saved in Google Drive, then you don't have to go through that manual process of downloading and uploading, because that's pretty much what we have to do, right? In these exercises also, if you remember, I'm sure you would have downloaded this. So first level you will download, next level you will upload, but that's a time consuming process. So instead, if you already have something saved in Google, you can mount your G drive and you can directly connect from Google. Okay, so this is a much more dynamic solution that we have here. So I wanted to show you both the approaches. So whichever works for you, you can try it out. So we load the data into a data frame. Class is my output column. So nothing much to talk about. Is the same process that we have discussed before. Okay, this is the same process. One more very interesting concept I would like to discuss here is the idea of the pair plot. Okay, this is the very conceptual thing. If you see, we have the class, which is the output column, and this is the syntax, how it looks like. We have sns.pairplot demo, diag kind equal to KDE. So the diagonal kind will be a smooth histogram. It's a KDE, which stands for kernel density estimate. It's a smooth histogram, and hue equal to class. Okay, so I can run the code in a little bit and show you what I mean to say. Okay, so let me run the code. These parts are not that important. Okay, you can ignore these parts. All I try to do here is I try to identify variables, try to do a little bit of data pre-processing, error handling, because I mean, this is the part that will usually keep going on and on and on, because there is no end to exploratory analysis. Whenever you see any data set, there will always be problems, and that is exactly what I try to decipher and find here. So I actually found that uh, the pressure feature, the blood pressure feature, there are values which are zero. So for example, if you look at the minimum value for blood pressure, it's actually coming out to be zero, which is not possible. I mean, even for the other columns, if you see body mass index, blood pressure, glucose level, this is the like the typical glucose level in the bloodstream, plasma level, that is zero. It's not possible that a person's blood pressure is zero, a person's BMI is zero. It's not possible unless you are dead. I mean, it's not possible. So most likely this is wrong data. And this is again kind of error handling that we are doing. See, Python will not complain. If you try to take this data and build a model, no problem. Everything will work fine. You will get a working model, but the results that you get will be wrong. Okay, so that's why these are the kind of things that will take time. Getting a basic POC out of the way is very easy. You can take a data, you can do model.fit, and you get the scores and you can show it to your stakeholders. Fine, project completed. But the things that take time are these iterative approaches that we are making. That New York City case study that I showed you, experiment one, experiment two, experiment three. That's the thing that takes time. You break it into weeks, you break it into sprints if you're doing a agile methodology, and you complete different chunks of work in different sprints. These are the things that will actually take a lot of time usually. Okay. Anyway, so this is a bit of error handling that I'm doing. You can go over this later on. Now let's come to this. This is the very conceptual part now. Okay. SNS.pairplot demo diag kind equal to KDE, Q equal to class. By the way, what is KDE? If I do it a little differently, let's say instead if I use hist, what will happen? This is the default actually. So if you say hist, I will get normal histograms. This is something we can relate to. So all the diagonals will be like histograms. If you just see, let this run. Seaborn is a high-level Python visualization library. That's what Seaborn actually is. So if you see, this is histogram. We can all relate to it. And we are breaking it by classes. Hue equal to class means color by class. Hue means color, right? Hue basically means color. So when I say hue equal to class, I'm basically saying, hey, color by class, color by the class column. That's the inference actually. Okay. So I'm treating histograms, but this is hard to see, right? I'm sure you can relate to me that if you want to do a visual analysis and a comparative analysis, it's hard to see. So what you instead want to do, you want a smooth histogram. That is a KDE. So KDE stands for a kernel density estimate. Mathematically, it's a probability distribution. Okay, but in simple analogous terms, it's like a smooth histogram. Okay, you're approximating the histogram, you're smoothing the edges, think of it like a smooth a density estimate of a histogram. Okay, yeah, I'm skipping the mathematics. There's like, we can spend entire day and talk about KDE. So we need to get into like things like probability distributions, and this is a density. It's like a probability density estimate, and that itself is based on confidence intervals. Some of you can relate to me if you're a bit aware of inferential stats. You can relate to what I'm talking about. So this entire thing is an estimate. So based on the actual frequencies of the histogram, so this is kind of a smoothing that we are doing. We're trying to estimate the exact edges of the histogram. Okay, so using confidence intervals, this is how it is actually created behind the scenes, but it's really not important if you're solving problems. If you This is what I meant, like this is the difference. Like, knowing the theory is useless. Now we can take the entire day and learn the theory, what is a KDE and how is it computed, but knowing that is useless, because when you're solving real problems, knowing what is a KDE will not help you. But yes, sometimes interviews ask you that question. Sometimes I really don't know why, why they do that. Because, my point is, if you're not applying a concept, then there is no point knowing it, right? What's the point in knowing something if you're not applying it? Okay, so yes, I mean, it's good to know, it's good to learn, it's good to be aware. Hey, I know what is KDE. It's good to feel great about it. But honestly, will you need to use it? Will you need to use that knowledge in real problems? Honestly, no. You just need to know how to use KDE. So oftentimes the usage is more important than just knowing the theory. What is it? Reading 2 pages of books and learning what is it? That's useless actually. Okay, let's understand how the KDE concept is getting used here. Let's see that. Okay, so if you remember, okay, another very interesting thing I want to show you is how you can kind of see this image in a different window. So right now you see the whole image is very hard to see, right? So what you can do is you can right click and say open a new tab. So the entire image will be rendered in the new tab. Okay, this is what this neat trick that all of you can use to see the complete picture. Okay, even within the Jupyter notebook, if you want to get a slightly zoomed in view, what you can do is you can actually kind of double click on the plot. See what I'm doing? I'm actually double clicking on the plot. You click on it once, you get a bigger picture. Click on it again, picture becomes normal. Click on it once, click on it again. Okay, these are some small neat tricks I wanted to share. Anyways, let's go back to the diagram. So what we have here is all the 8 different variables, and the colors basically stand for the classes, right? What are the classes we have, friends? We have 2 classes, if you remember. So I'll take a different color. So we have the class blue, which stands for not diabetes, and the class orange, which actually stands for diabetes, D. So the class orange stands for diabetes D, and the class blue stands for not diabetes ND. Now, what is the concept around it? What are we looking at here in this diagram? Let's see that. In this diagram, we are able to visualize the separation between the classes. There are 8 features, right? We have features starting from pregnancy, plasma, pressure, all the way up to age. So we have 8 different features in this particular data set, as we can see here. What we are able to see here is uh, the separation between the classes across all these features. So whatever features we have across all the features, we are able to understand how the classes are separated across all these features. How are the classes separated across all these features? That's what we are able to understand. Okay. So for example, if you look at the second feature, the one that I was highlighting, you can see the screen now better. If you see the second feature, this is the plasma feature. Remember, plasma stands for glucose. This is actually nothing but the glucose level. Glucose, how we measure glucometers, use glucometers in our homes to measure diabetes levels. So glucose level. So it's like a glucose level. Think of it that way. Okay. What it tells you is, and again, ignore the y-axis. The y-axis is like a frequency. The x-axis is the glucose level. This is the way you read the plot. The x-axis is the glucose level, and the y-axis is the frequency. Maybe if I show you in a better way. So this is the glucose level, GLU. This is a distribution plot for not diabetes. So you can see for all the not diabetic people, what are the average glucose levels? And this is showing you the distribution plots for all the people who have diabetes, D. And you can clearly make out, so I've just drawn this diagram in a bigger way here. You can clearly make out that people who are diabetic on an average have higher glucose levels. That is the interesting part. And that's how we are able to visualize the class separation, right? So in a way, we can say that, hear me out very carefully, what I'm about to say. We can say that glucose is a good predictor of diabetes. So by looking at this diagram, we can say, because the classes are well separated, the diabetes and not diabetes classes are very well separated, we can say that glucose is a very good predictor of diabetes status. If I know that the glucose level in the person is high, I am fairly confident that the person is diabetic. And if I know that the glucose level in the person is low, I can be fairly confident the person is not diabetic. So the glucose level in the bloodstream is a very good predictor of diabetes status. And this is very similar to the idea of correlation coefficient that we talked about yesterday. So in regression problems, we use correlations. So you remember the advertising data set we did, even today, the concrete data we did. Advertising yesterday, we saw that TV and sales had a very strong correlation. So it was like saying that, okay, TV is a good predictor of sales, right? Similarly here, when we are solving the classification problem, we will look at this data. We will do the initial exploratory analysis, what we are doing right now. We are creating some plots. We're trying to understand our data better. And we can say that, yes, indeed, glucose is a very good predictor of diabetes status because the classes are very well separated. If I know the glucose level in the bloodstream, I am fairly confident that, yes, the person has diabetic. If the glucose level is more, the person is most likely diabetic. And if the glucose level is less, the person is not diabetic. So the glucose level in the bloodstream is a very good predictor of diabetes status. The more the glucose level, higher the probability of diabetes. Lower the glucose level, uh, lower the probability of diabetes. Okay. The same applies for some other features. I think if you see, there's another feature called body mass index. It's not as prominent, but you can still see the orange part is a little separated. Can you see? If I try to separate it out a little, the blue part is kind of this way, and which makes sense, no? Which makes sense that people with higher BMI are typically more prone to diabetes. I mean, it's like generally diseases. If you have a high body mass index, and it's like maybe it's more prone to obesity probably. High BMI is not a good thing, right? So if you have a higher body mass index, then maybe that is more prone to diabetes. Okay, so maybe it makes sense, and also to some extent age as well. If you see the last feature, age, uh, it is overlapping. It's not a very clear separation, but you are able to kind of see some semblance of separation. Maybe people with higher age, uh, like if you draw the distribution plots here, the average age for diabetic people is somewhere here, and the average age for not diabetic people is somewhere here. So you can see very clearly that there's a very clear separation that we can see uh, between the classes. So if you're older, you're more likely to be diabetic. And if you are not that old, if your age is lesser, then you're less likely to be diabetic. Okay, so very good takeaways. We are able to, like, we just now studied what is classification. Classification is where you are trying to separate the classes. Remember, we're trying to find a model or a decision boundary that separates the classes. And here we are able to get a very nice pictorial understanding of how to identify good quality features. Okay, so this is a very good application of how pair plots are used in practice. Okay, so you can visually make out that, okay, some features are seemingly important, but some features are not important. Like, for example, blood pressure. Look at this feature called blood pressure. Okay, so if you look at this, the blood pressure feature, very interesting. The blood pressure is not a good feature. This is a pressure feature. Can you see? So if your pressure is high or your blood pressure is low, blood pressure usually has nothing to do with diabetic status. Okay, because pressure is dependent on other factors. If your pressure is high or if your blood pressure is low, the person may be diabetic, may not be diabetic. You're not able to see a very good separation between the classes. So these are bad features. If you eventually want to build a classification model, your objective should be to drop these kinds of features. You should actually drop these kinds of features like blood pressure and all this, or maybe even skin thickness. These kinds of features you will drop, but you want to take these kinds of features, feature selection. Okay, so all this is part of data pre-processing. So we talked quite a bit about data pre-processing, ideas of data pre. All this is ultimately part of data pre-processing. So you'll go and uh, identify good quality features, add new features like what we did for the New York City problem, taxi problem, uh, select important features. Part of what we did yesterday, we took TV, radio, we ignored the newspaper feature, the correlations were low, remember? And part of what we are doing now. So you can see very clearly glucose is good, it's a good feature, but the pressure and skin is not a good feature. So we don't want to include these features in our analysis. If we do that, then the model will not be good. The models that we end up building using these features will not be good. Okay, so we need to remove the noise and other things like skewness, encoding, scaling, all of these are pre-processing techniques. So you build the baseline model and try all these different things. So now try to add features, remove features, select the top features, scale the features, transform the features, remove the skew, remove the outliers, encode the features, convert your categorical values to numbers, and try to build different models. And by the time you complete your machine learning experiments, you would have built hundreds of models. Okay, believe it or not, you would have built thousands of models. What if I say you would have built tens of thousands of models? So by doing different experiments, you would have built tens of thousands of models before your final model makes it to production. POC is easy, but these are the experimentation parts that actually take time. But I hope the idea is clear. What is it? Now, obviously, it's very hard to visually make out what's going on. It's not practical to look at a diagram and say, hey, I think I see a good separation, because it's not practical. So what is the quantitative way to do it? There are a couple of approaches. We use some statistical techniques like p-values, which I don't want to get into right now, but it's not very used also. But p-values are one way to do it. The other way to do it, other more practical technique that is followed is this thing called feature importance. So we use something called feature importance to basically identify how important a feature is. So you can use something called a feature importance. And you see, I have listed out my features right now. And with respect to that, you can see that, okay, this feature is the most important. Okay, so the concept we have understood. How do we implement it? It is implemented using something called feature importance. So feature importance is something that will give you a mathematical value. It will tell you something about what is the importance of the feature. Again, this is calculated in a very different way. Some of you who know decision trees, who know random forests can relate to it. I think you guys know that there are entropies and all these things, how this is calculated. So that is a different conversation. Don't worry about that. This is the application. Next time you get any data set, what you can do is you can straight away compute a feature importance, and that feature importance will tell you how important is that feature in predicting the outcome. Okay, so it is kind of giving you the correlation between X and Y. Think of it that way. It is kind of giving you the correlation. So all these values will add up to 100%. So if you add up all these numbers, they will add up to 100%. Okay, and you're trying to identify which are the top features. So out of all these features that we are seeing on the screen, which are the top features? Which are the features which are having the highest correlations or the highest importance? And you can clearly see, very much in line with what we covered, you can clearly see that the top features are plasma. Plasma is the best feature because we saw the best separation here, right? Then we have something called body mass index, BMI. This is the third last feature. And then we have something called age. This is the, as you can see, we saw this exactly in the class also. All right, now let's move on. Let's come to the actual modeling. All this was the pre-processing and all that, right? This is a never-ending process. It goes on and on and on. So we have to move on, right? So let's move on. So next, what did we do? Next, we went ahead and we are building the regression model. You can the classification model. You can see very basic, same thing as we discussed before. So take the data, split into training and testing, X train, X test, Y train, Y test. So we do the train test split and we use an algorithm called logistic regression. So this is the new algorithm that we are using. We are using a new kind of algorithm called logistic regression. And we fit the model on the training data. We do dt.fit X train, Y train, and we do the predictions. This part is exactly what we talked about, and we also get the cross-validation scores. So why do we do cross-validation? Because remember, I told you that we should not trust the test accuracy. Okay, so we should not trust the test accuracy. So cross-validation is what we are using to get 10 different accuracy scores and take the average accuracy score. So we are doing cross-validation to generate 10 different accuracy scores, and in turn find out the average accuracy score. So that's what we are doing as part of cross-validation. Okay, so that's the whole idea of what cross-validation is. Okay, so once again, so what is the nature of this model right now? The training accuracy is 77%, and testing accuracy is 76%. So this is like a kind of an underfit model. It's not a very good model, but we can say it's a kind of an underfit model that we are getting. Okay, so you take some data, you build a model, and we are getting a kind of an underfit model where the training scores are low and the testing scores are also low. We're getting a reasonably underfit model right now, and we are trying to make it better. Okay, so we'll see how to make it better. But obviously, everything else that we saw here in the code is exactly what we saw. There's nothing new. The only different part is we are using something called logistic regression. The logistic regression is what we do the classification part. Okay, so the only difference is that instead of linear regression, we are using something called logistic regression. Okay, there are other kinds of algorithms that we also have for classification. So in this notebook, we will see what are the different algorithms that we can try out. What are the other algorithms that we can try out? You do not need to get into the theory, not needed, but understand the application. That is most important. Okay, so how to use, what are the things to look out for? Okay, because one of the things that I have figured out by taking these sessions and by teaching a large number of people over the years is, honestly, it doesn't help. Like, only area where I've found it is useful is maybe to some instance in cracking interviews, where they sometimes ask you questions about, hey, what is X and what is Y? That's where all these 1 year, 2 year long university programs come in. But when it comes to the real world, when it comes to actual application, okay, I know of no data scientist who actually goes and thinks of logistic, hey, this is the math and this is when they apply it. You have the libraries with you have the frameworks with you, you go and apply it. Because you have to understand, and you have to understand, machine learning is a largely experimental domain. Given any data set, there is no way of saying what algorithm will work. You have to try it out. You have to build a model, you have to try out, you have to see what kind of accuracies you're getting, and only then you can be certain. Like, let's say, even yesterday's exercise, a concrete, there was no way of knowing in advance that, hey, my data is having a non-linear pattern. There's no way you can say that. No way. Unless you can perform statistical tests, but generally you have to build a model, you have to experiment. You take the data, build a model, build a linear model. You saw you were getting 60%. You tried a different technique, you got 80%. You tried gradient boosting, you got 90%. Sorted. That's it. That's the way how we actually do it. Okay, so even by knowing the mathematics of gradient descent or knowing the mathematics of gradient boosting would not have helped you get extra 2%. You will still have to use sklearn and call the model. Right? So again, you have to understand which are the avenues where the math and science is needed. Okay, unless you're in research, unless you're actually working at a class level. And that is also an important skill. As I told you, there are people who are working on, because these are open source libraries we are using, right? But sometimes you will want to use custom algorithms. You want to develop algorithms specifically for your data set, specifically for your problem statement. So maybe there are different variations of decision trees that you want to use with different loss functions. So decision tree algorithms use different loss functions. You want to use a different variant of a decision tree. You might have a different use case. You might want to build a different variant of a gradient boosting algorithm for your organization. So what you will do, then you are back to concepts of object-oriented programming. You will go to sklearn, because see, all these are classes, right? If I show you, like this is the same thing I was talking about a little yesterday. So if you go to gradient boosting, these are all classes, right? So somebody would have come up with this algorithm. This is sklearn gradient boosting regressor. And if you click on the source, you will see the entire source code. This is a huge class. Somebody had to write it, right? Look at this. You count the number of lines of code. Huh? This is 2,192 lines of code. Are we doing any of this? No, we are using it. But somebody has to write it, right? So two things. Somebody had to understand what is gradient boosting. Somebody had to, create the algorithm mathematically. Statistically, they had to do that thing. And then you need a developer to actually convert this into classes, right? So both are important skills, right? I'm not saying that this is not important, but my point is, from an application perspective, this is useless. In the day-to-day work, day-to-day real-world application, you will not be, like, required to understand what is the decision tree and what is the gradient boosting to solve business problems. That is a very different skill set. I know a lot of people who are very good in theory. They are brilliant in answering questions, but when you give them problems, they fail. Another very interesting insight I wanted to share, because these are all studied and tested strategies, right? Typically, people who do very well in Kaggle is a competition website. Okay, it's the same website where we took our data sets from. Typically, people who do very good in Kaggle, they are very good in solving competitions. They are very good in hands-on. A lot of hands-on is about getting the work done. I give you a problem statement. I don't care what you do, how you do, just solve the problem for me. Trust me, it's a very different skill. Okay, it's a very different skill. So you have to approach that from a very different mindset. So when you're solving real problems, when you're solving real competitions, your focus is on time. You don't have the entire day. Research is very different. Research is where the company is funding you for 3 years. But real production, the client is only funding you for 7 days. You have limited time. And in that limited time, you have to go and get a certain accuracy and get the job done. I don't care what happened, how it happened, what it is. Try different things. You have a limited amount of time. You have lots of constraints. You work within that constraint zone, and you get the job done. So there are very different skill sets. Okay, just wanted to clarify that, because when you look at all of these things, right? When you look at all of these things, you know, uh, this is a very different world altogether. So okay, so don't be intimidated. Like although you were able to use gradient boosted decision trees in the class, you were able to build the model behind the scenes. This is all that is happening, but you don't have to worry about it, right? So just wanted to absolutely clarify that part. Okay, yeah. Anyways, so moving on, this is the logistic regression model that I have used here. Okay, now next up, let me show you. We are trying out a gradient boosting classifier. This is a variant of a classification algorithm that we are using. Okay, just like we had gradient boosting regressor, similarly we have something called gradient boosting classifier. Okay, so this is like a non-linear classification algorithm, just like we have gradient boosting regressor, which is a non-linear regression model. Similarly, we have gradient boosting classifier, which is a non-linear classification algorithm. N estimators will be a hyperparameter, but one key learning is that the model is little better. I think you can clearly see that compared to the linear logistic regression model, the baseline model, which is giving us 77, 76. If you see, the gradient boosting is giving us 83, 79. It's not great. It's not brilliant. It's not as high as concrete, but I think you will still say, we can still say that we have incrementally built a better model. This is a model that is working out better than what we had. Okay, so this is the incremental improvement that we are able to get here. Okay, now let's see what else we have. And what I'm trying to do in this notebook is I'm trying to clarify a lot of the classification concepts. Okay, the first part is good. We are sorted. You can see there's nothing different we are doing. Cross-val scores and all this is very similar. Now let's move on. What are the different ways we evaluate a classification model? Now this part is important. We talked about train accuracy, we talked about test accuracy, but what else? If you look at this particular exercise right now, what are we doing? We are effectively trying to predict, does the person have diabetes or does the person not have diabetes, right? So, and if you go by the different steps that we covered, we take a data set, we take a training data, split the data into training and testing. On the training data, we build a model. And on the testing data, the mock question paper, as we call it, we evaluate the model. Okay, so we build the model on the training data and we evaluate the model on the unseen test data. So that's what we actually saw. Now, what else? What are the different ways we can go and evaluate the model, especially in the world of classification? And this is what leads us to a very, very interesting topic called the confusion matrix. Okay, so this is going to tell us how we evaluate a classification model. So using a confusion matrix, we can actually evaluate a classification model. This is going to be a bit of a deep topic. And what I will do is I will just pause for a couple of minutes. I will allow everybody to go through this diagram. Don't have to worry, I'll explain every part of it. But this is exclusive to classification. Okay, so until now, what were the ideas? All the ideas are very similar to what we discussed for regression, right? So the dot fit, the cross-val scores, they're all very similar in code. And again, our focus is from a code hands-on concept perspective. We're not trying to get into theory. Okay. Another interesting concept was we talked about the pair plot, feature important. That was little new for classification. This part is completely new for classification. You don't have this for regression. Okay, so give it a glance. Then I will explain in detail to you what is true positive, false negative. So next time you talk about, you're working on your networking devices, right? You're working on some network intrusion detection, classification models. So you say false positive. What is false positive there? Model predicted is a threat, but in reality, it's not a threat. So these are very, very important conversations you need to have with your customers. So next time, you deploy a model, your customers will ask you that, hey, you built a classification model for me. Please tell me how many false negatives we have in the model. Okay, so we need to understand what these different jargons are. So now we look at the confusion matrix, which can be used to evaluate a classification model in a bit of a detailed manner. So far we have understood how to use just the accuracy metric to evaluate a model. And now we will look at something called the confusion matrix. So how can we evaluate a model in a lot more deeper manner? So we are taking the same example. We're taking the same use case here, the diabetes classification problem. And one of the first things that we do is we try to define some conventions, right? So whenever we are doing any classification task, we try to define some conventions. So here we are saying that we have two classes. One, we have a not diabetes class, which is 0, which is a negative class, which is we are labeling this as 0. And the second is a diabetes class, which is a positive class, which we are labeling as 1. Okay, so again, we have got two classes. One is the class not diabetes, which is 0 negative class. And the second is the diabetes class, which is 1, which is positive class. These are two classes that we have right now. And the objective of this exercise is we want to predict. The objective of the exercise is we want to predict whether the class is negative or positive, whether the model predicted diabetes or not diabetes. Okay. So this is what the confusion matrix looks like. All of you can see the screen. So the confusion matrix is basically a kind of a array. It's a kind of a metric structure where along the rows you have actuals and along the columns you have predicted. Now, where is this actual and predicted coming from? Because remember, this entire thing is coming from the training data. So first we use the training data. We build a model on the training data. So we do model.fit xtrain ytrain. So we build a machine learning model. And then on the testing data, we do the predictions. Okay, so on the training data, we build a model. So we build a model on the training data. And on the testing data, on the X test, we do the predictions. We get the predicted values on the testing data. So we are trying to test the model, right? So we try to get the predicted values on the testing data. And we try to compare those predicted values with the actual values which are part of the test data, because it's a testing data. So if it's a testing data, we know the actuals also. That is what we are comparing. We are comparing what the model predicted with what the actual results are. So remember, there are two classes. We have class 0 and class 1. So class 0 means not diabetes, and class 1 means diabetes. So the model will predict two values here, 0 and 1. And the actuals are two values, 0 and 1. And this is how we get the confusion matrix. And with respect to this, there are a few different terminologies that we get right now. We have got TN, TP, FN, FP. So TN stands for true negative. True negative means model predicted negative and prediction is also true. So a true negative will be somewhere here. This is the way to understand true negative. True negative basically means the model predicted negative. So the model predicted N, it predicted negative class, and the prediction was true. Actual was also N. So that means predicted is 0, actual is also 0. That's true negative. What is true positive? True positive means model predicted positive and the prediction was true. That means model predicted 1, actual is also 1. That's true positive. So in this data set, you've got 35 TPs. There are 35 cases where you predicted 1 and actually also it's 1. That means these are 35 cases where the model predicted diabetes and actually also the person has diabetes. So T and TP are fine. They're absolutely okay. And in fact, whatever we were discussing all this while, like accuracy, the test accuracy rather, test accuracy is nothing but Tn plus Tp by total. This is actually what we were working with all this while. We never looked at Tn separately, Tp separately. We were only looking at the accuracy metric, right? Now, what is accuracy? What exactly is the accuracy metric? Accuracy is Tn plus Tp by total. So out of total 154 observations, there are this many correct negative predictions plus this many correct positive predictions. You're able to clearly see how many correct negative predictions, 88, plus how many correct positive predictions, 35. That is how we understand the meaning of an accuracy. But what is really interesting to know is the false positives and false negative, because this is the errors. Whatever you're seeing in green are the correct predictions. These are correct negative predictions. These are correct positive predictions. Whatever you're seeing in red are the incorrect predictions. So false negative means that model predicted negative. This is false negative. Model predicted negative and the prediction is false. So what is false negative? Model predicted negative and the prediction is false. Actually is positive. So model predicted 0, but actually it's 1. This is a very dangerous case, right? That is what confusion matrix will tell you. You can build a model and now you can understand more explicitly how the model is actually doing. You can really understand these kinds of dangerous cases. You can clearly see that, okay, We can understand these dangerous cases very explicitly now. So you can clearly see that, okay, the model predicted the negative class, and the model predicted you don't have diabetes, but in reality you do have diabetes, which is a very dangerous case. This is a scenario where somebody who actually has the disease, but the model is missing out. The model has missed out completely the case where the person actually has a disease. That is what we refer to as false negative. Okay, what is false positive? False positive is like a false alarm. Okay, so false positive is like a false alarm. So we are seeing something called a false positive, which is nothing but a false alarm. And you can clearly see the false positive, which means that, okay, model predicted that you have diabetes, but in reality you don't have diabetes, right? Which is I think which is okay. When in medical terms, that's, yeah, I mean, it's an error, of course. It's something where we can say that the classification is not happening correctly. It's a mistake. A mistake is a mistake at the end of the day, however you try to justify. So FP is also a mistake, but it's a mistake that is more acceptable in the medical community. I mean, if you consult a doctor generally, I mean, as an example, let's say you have some cough and cold and you go to a doctor, the doctor is fine to, like, see, I mean, it's important for the doctor to not to miss anything. They might tell you that you might have a medical condition, give you 100 tests, because they want to be sure that they don't miss out anything. So in the medical fraternity, FP is okay, it's acceptable. FN is not okay, unacceptable. Even a single false negative is deadly, because this is the case where the model predicted you don't have a disease. You couldn't even diagnose the medical condition, but in reality, somebody has it. You see how important it is to know which error is costly. So ideally, FN and FP both are mistakes. Ideally, FN and FP both are kind of errors, but it's important to understand conceptually which error is kind of considered more costly. So we have to look at both these errors, and we have to understand which error is more costly. Which error is more costly? Is FN more costly or is FP more costly? And we have to mitigate the errors accordingly. So whichever errors are more costly, so we have to mitigate those errors accordingly. Okay, so that's an important thing to keep in mind. So if we think that in a particular business case, if you look at network intrusion, like if you work with, let's say, a lot of network data and network threat detection, cyber security use cases. So in those kinds of use cases, again, false negative is very costly. FN is very costly. FN is unacceptable, because FN in that case would mean model predicted it is not a threat, but in reality it's a threat. See, the whole idea of cybersecurity is to prevent threats. Like, I mean, if you have a false negative situation, that's the most dangerous situation out there. FP is almost like it's accepted. False alarms we are all okay with. There'll be a lot of cases where the network will give you a false alarm. Like, if you're using antivirus products, oftentimes it will say that, hey, I think if you're using unsafe Wi-Fi's, or if you try to go to a website and some dangerous HTML is detected or some JavaScript is detected, the browsers will often warn us, or the add-ons will often warn us that, hey, I think it's a threat, so the website will not open. These are all false positives. In reality, it's not a threat, but the model predicted it's a threat. That is okay, but this is not okay. So the confusion matrix will help us understand things at that level. So far we were working with just accuracy. Accuracy was basic. Accuracy was giving us an overall picture, like, hey, on an average, how accurate is the model? So this was giving us kind of like an overall picture. So on an average, how good is the model? That was accuracy. But the moment you look at confusion matrix, now you have more granular control. Now you have more granular control into the things. You are able to understand the things more in a much more granular manner. You're able to understand the things in a more accurate way. Okay, this is the idea of the confusion matrix. Okay, so you can look at false positives, you can look at false negatives, and iteration one baseline model. You can see what kind of FN and FPs you're getting, and then you can do some feature engineering. You can try to use a better algorithm. You can try to add some new features, reduce the irrelevant features. Like in diabetes, we have those. We have got a lot of irrelevant features. Remember, blood pressure, skin thickness, they are not important features. So iteration two, you can remove some of these irrelevant features and rebuild the model. Iteration three, you can do something else, rebuild the model. So you can try out different methods, and you can rebuild the model in different ways. And every iteration, you try to see what are the FNs and FPs you're getting, and you try to make the model better and better and better. So that's the whole idea of what the confusion matrix actually brings to the table. And similar to that, you have other metrics like precision and recall, which are kind of like class level accuracies that you can also track. So that's exactly what I did here also. So you can say see the code behind the confusion matrix. So initial part is the same. We take the data and we split the data into train and test. And on the training data, we fit the logistic regression model. dt.fit xtrain ytrain is what we do. And we compute the training accuracy and the testing accuracy. And we calculate the cross-val scores. You can see this is the cross-val scores that we computed. And towards the end, this is the code for the confusion matrix. So very simple. So based on whatever model that we have trained, the model is dt. So we simply say dt.predict of x test. So first we calculate the predicted values, right? So based on whatever model we have trained, first we calculate the predicted values. So on x test, we calculate the predicted values. And in the confusion matrix, we are simply comparing the actual values with the predicted values. So the confusion matrix is nothing but a comparison of the actual y's with the predicted y's. So we are comparing the actual y's with the predicted y's. So that is what we are doing in the confusion matrix. Okay, that's the idea. And if you see the confusion matrix right now looks somewhat like this, all of you can take a look at it. And this is exactly what we talked about now. We can relate to it. This is my 0, this is my 1, and this is my 0, this is my 1. 0 means not diabetes. This is the convention that we define here. And this is the actuals along the rows, and this is the predicted along the columns. Okay, so we can clearly see this is the number of FNs. So we have 24 false negatives. We have 24 such cases where model predicted you don't have the disease, but in reality, you have the disease. There are 24 such cases where model predicted you don't have the disease, but in reality, you have the disease. And there are 10 such cases where model predicted you have the disease, but in reality, you don't have the disease. There are 10 such cases. So there are 10 such cases where model predicted, yes, you have diabetes, but in reality, you don't have diabetes. So that's the inference we are able to get right now. Okay, so this is very important. And what we can do is now we can try different models. So now we can try if you just see we can try different models and we can compare. So we can build a gradient boosting model and we can compare the FN and FPs for those models. Few other important ideas for classification. So this was another new idea that we learned with respect to classification called the confusion matrix. A few other new ideas is something called predict proba. Very important. This again was not there for regression. This is only for classification. Okay. What are the different steps for model building? First, we take the data, we build a model, we train a model on the training data, and then we do predictions on the testing data. Until here, we are sorted. Even in regression, we were able to do this. We were able to get the predicted values on the testing data. Additionally, in classification, what you can do, you can also get the predicted class probabilities, because that is what classification is inherently doing behind the scenes, right? So here also what we have done, if you see, we have already trained a machine learning model on the training data. We have done dt.fit on x-train, y-train. So that dt.fit we have done. We have already trained the decision tree model on the training data. And now we want to use that decision tree model on the testing data and find out the class probability. So what is going on behind the scenes here is, if I just annotate this a little better for you, this is the 0 class and this is the 1 class. And if you see what's going on here, we already have trained the classification model. This is the logistic model. So we are looking at the first row of my X test. So based on, and see, this is the testing data. So the Y is missing. We only have the X here, right? So we have to predict the Y. So given this new observation, we are trying to do the prediction. So based on this new observation, imagine this is like your decision boundary. We talked about that, right? So this is like the class 0, this is like the class 1. This is the 0 side, this is the 1 side. So given a new data point, you are trying to predict what is the probability it is on this side and what is the probability it is on this side. That is all you're trying to do. You're trying to find out the probability, how close it is to the 0 side and how close it is to the 1 side. That is the intuition of what we are trying to do here. So, and that's how we get these class probability values. So given a new person, given a new patient, we have a 45% probability this person is diabetic. And obviously 100 minus that is 54.74% probability is not diabetic. So we in addition to just getting the labels, we are also getting the actual class probabilities. Okay, so you can see the fourth person. The fourth person is this one. This person apparently has a very low plasma value, right? 61 glucose level is very low. So this is like extremely low. This the glucose, I think sometimes even very low sugar is bad, right? So this is very low glucose level, and because the glucose level is so low for this fourth person, you see for the fourth person there is only a 3.98% probability of diabetes. Okay, you can see how beautifully the data is correlating. So we are looking at the features of a new observation, and we are able to find out the probability the person is diabetic and the probability the person is not diabetic. And what we can now do is we can use these probability values and we can write our own custom prediction. We can, so we can build the model, we can get the predict proba values, and now we can write our custom if else statement. We can say, hey, if the probability of diabetes is more than, we can use a parenthesis. So if it is more than 0.2, so if anybody's diabetic probability is more than 0.2, then classify that person to be diabetic, then diabetic. Okay, so let me, yeah, so then diabetes, else not diabetes. See what I'm getting at? I've reduced the thresholds. I have reduced the thresholds because remember, diabetes is a deadly disease. It is a deadly disease. So even if there is a slightest of chance, even if there is a slightest of possibility that a person might have the disease, I will still warn the person. I don't want to take any risk. Even if there's a slightest of possibility a person might have diabetes, I will warn the person that, hey, you might be diabetic. Even if you have a 20% probability of diabetes, I will still classify diabetes, else I will not. So you can write your own custom if-else statements based on the probability values, right? So how does it really happen in sklearn behind the scenes? Because obviously our focus is scikit-learn and we are using that library. In scikit-learn, there is a default predict function. There is a default predict function. This will work based on the 50% threshold. Okay, so you can write your own custom thresholds, which is what we do in practice. If you're trying to solve real business cases, you will write your own custom if conditional statements for the prediction. But in sklearn, if you're using sklearn.predict, what will it do behind the scenes? Behind the scenes, it will use the 50% threshold. So it is going to compare with the 50% threshold. If the probability is more than 50, it is diabetic. Else, if it is less than 50, it is not diabetic. This is what it will do behind the scenes. Okay. Rest of the workflow, we are going over different algorithms. So here I tried a decision tree classifier, and in all these cases, very interesting to note would be not just the train and test accuracy, but you can look out for the false negatives. For example, you can look out for this one. So very clearly with a logistic model, I was getting 24 false negatives, and you can see that gradually, as we try different algorithms with decision tree, I'm getting only 20 false negatives. So you can see incrementally we got a better model. This is what we are trying to improve right now. So now all of a sudden, it's not just the overall accuracy that matters, but what is far, far more important is the false negative. Because remember, maybe let's say this could be an agreement you have with the customer that your test data set, even if there is a single false negative, we cannot allow, because even a single false negative can be very deadly. Because our classification model, we cannot allow to miss anybody who has diabetes. So it has to be that accurate. Okay, so sometimes machine learning model testing is very, very important, because that is how you go back to your customers and you show the results to your customers. There'll be a customer side testing that they will do. They will take some sample data from their end and they will give you a confusion matrix report. So this confusion matrix is very, very important. It's a very important part of any research papers or model testing. So and you will often talk to your customers in these terms. You will say, okay, this is the number of FNs I'm getting. This is the number of FPs I'm getting. Okay, like that. Rest of the parts are very similar. I think there's not much to talk about. This is the gradient boosting classifier I'm using, and you can see this is the hyperparameter and estimators that I'm using, and very clearly gradient boosting is a better model. So my not only is my accuracy numbers up, but also my false negatives are much lower. Okay, so see the incremental improvement that we make. Okay, and another very interesting learning from this exercise would be that no matter what you try, beyond the point you cannot get very good results. And that's just the nature of my data. Something that you have to accept. Okay, there's nothing we can do about it. No matter what we try, beyond the point, I cannot get very good results, because my data itself was so bad. If you go back to your original data, the data was very bad. If you remember, the classes were highly overlapping. Although we saw that there were some features which were good, the plasma features seemed to be kind of good. But even then, I mean, how do we define good? Like, it's not a very good separation, right? I think you can relate to it. The separation isn't that good. I mean, it's an okay kind of separation. It's not a very good separation, right? That is one thing that you have to keep in mind. We are not seeing a very good separation between the classes. So whatever you're seeing on the screen right now, we are not able to see a very good separation between the classes. So the separation is kind of okay, but we aren't seeing a very good separation between the classes. That's important to keep in mind. Okay, so you can see this is the blue class, this is the orange class, and I mean the other features you have pressure, you have skin thickness, you have test, you have body mass index. So all these other features that you see, these other features, if you take a look at it, the separation is not that good between the classes. So we are not able to see a very good a separation between the classes for these other features. That's an important thing to keep in mind. So that is the reason, and that is the primary reason why. That is the primary reason why, if you when you're building the models, you're getting such a even something like a gradient boosting model, you're only getting up to an 81% accuracy. So despite you might be wondering that such a powerful algorithm, why am I getting only 81%? Why not more? Why are the false negatives 18? Why can't it be close to zero? And it's difficult. No matter what you do, beyond the point, if your data is bad, the models will be bad. There is nothing you can do about it. That's why in data science, the data is such an important part. You need to have the right set of features. The inherent data has to be good. Only then the algorithms can model it. Okay. If you just have a powerful algorithm, nothing will work. If your data has to be right. That's why we put so much emphasis on data pre-processing, feature engineering. You know, so model building comes much later generally. Okay. So just one small pointer I wanted to mention. Something I mentioned at the very end. This is a process of hyperparameter tuning. If you remember, I told you that all the different algorithms that we have. So maybe decision tree is slightly different. We have talked about an estimator. So let me use this with respect to uh, tune the hyperparameters. Tune the hyperparameters. It will try to generate the code the same way. You'll be surprised, like how it does it for the gradient boosting classifier using grid search, CV, and it will actually try to tune the hyperparameters of the gradient boosting classifier using this thing. I think it's really made it too complex anyways. So what we can do is we can actually go and tune the hyperparameters of any algorithm, okay, using something called grid search CV. If you remember, I told you that hyperparameters are these tuning knobs. So decision tree is a kind of an algorithm. It has something called depth. I will talk a little bit more about decision trees very briefly in tomorrow's session. I will recap that idea once again for you, what exactly it is. Okay. So right now we're just kind of doing this at a very application level, at a very hands-on level. But what is it? We will have a small discussion on that. I will talk about that also very briefly. I'll come to that. Okay. So decision tree has a hyperparameter called maximum depth. Random forest and gradient boosting, they have hyperparameters called an estimator. So different algorithms have different hyperparameters or different knobs that you can tune. Okay, you can go to any algorithm and you can tune the different knobs in the algorithm. You can tune the knobs in different ways. Okay, so you can tune the knobs of the algorithm in different ways. Excuse me. That's the whole idea, right? That's the whole idea here in this case. So the concept is somewhat like you use something called grid search CV, and you use uh, the maximum depth here. This is the decision tree hyperparameter, and you set a range 2 to 10. And all that you're doing is you're finding out that so it's like you're taking different values of maximum depth, and you're finding out what is the best maximum depth. So that is what is basically happening behind the scenes. So I think this is not defined right now. So we can go and if I define the decision tree classifier from sklearn sklearn.tree, import decision tree classifier. If I just do that, so the model will actually tune the hyperparameter. So grid search CV is also not defined. So let me just go and from sklearn dot model selection. Okay, import with series. I think some of the code went away most likely. That's why it's giving this issue. So see, whenever we have a tick mark basically means that the kernel, the cell is successfully executed because I did not execute the remaining cells. That's the reason why we're getting this error. So let me run this, no problem. Let me run this. So I'm going to just quickly run this code. So now X train, Y train, X test, Y test is set. This is all that we wanted to do. Let me just run this code. And now we can go and we can scroll all the way down. And now I can use this. So what it will do behind the scenes is it will go through the different hyperparameter values. Okay, we can use anything. We can use decision tree. We can use gradient boosting. Okay, if you're more comfortable with gradient boosting, because that's what we have done in the class, right? So we have used something called gradient boosting. So let me change it back to gradient boosting. So and gradient boosting has a hyperparameter which is n estimators, right? Excuse me. And we can take a range of 2 to 100 in increments of 10. So what it means is, we're taking different values of n estimators. It could be 1, it could be 11, it could be 21 in increments of 10. This is a step. Okay, so this is the min value, this is the max value, and this is a step. Okay, so it's like you're trying out different values of n estimators. You're trying out different values of n estimators. You're building different models, and you're seeing that for which model, for which n estimators value, we have the best accuracy. That is quite literally what it is doing behind the scenes. So if I just run the code, I think this is gradient boosting classifier. It will take a little bit more time behind the scenes. Let me call it gradient boosting classifier. And you can see very clearly, it has given me that the best one, okay, if I run the code, you will see the best one is actually n estimator 31. So this is the way how you will do this in the real world. You will take the training data, you will take the algorithm, and you will first decide what is the best algorithm, and then you will decide what is the best hyperparameter for that algorithm. And once you know that, okay, n estimator 31 is the best one, once you know n estimator 31 is the best one, now what you do? Now you build a full model. You build a full model on the whole data. Fingers crossed. I think Gemini should generate the code. Let's see. But if it doesn't, I'll write it for you on the whole data. Let's see. I think it should understand what I mean to say. But I think unfortunately it does not. It does not. I'll have to explicitly write it. Anyways, no problem. So we will use gradient boosting. Hopefully, if I give it a little bit of help, it will figure out. But these are some, these are obviously, it's not that machines will understand everything today, but it's a phase. So, and I think it should understand, but it still didn't actually. If you see, dot fit, X train, Y train, X train, Y train, and now this is the final model. So this is how I'm building the final model, and then I will calculate the accuracies and all that. I think by now it will, yeah. I mean, this part it's able to figure out, but the initial part it wasn't. So now I can calculate the train accuracy, test accuracy. This is the best model I got so far. Okay, so and remember, the cross-val scores are also important. I can get the cross-val scores. Hopefully, it should figure out. Yes, it does it. So yeah, so we can get the cross-validation scores. Okay, so get the average cross-val score. So what is the average cross-val score? Okay, see, I'm just typing average. I'm just starting to type average. It's figured out. It figured out what I wanted. So did a nice job, right? Yeah. So look at this. Yeah, decent. Let me remove the confusion matrix. It's not required. Yeah. So this is the end-to-end, right? So the important learning here was how we tune hyperparameters. Okay. So first part, we take the data, we do the pre-processing, we identify good features, we try different algorithms, decision tree, random forest, gradient boosting, logistic. We try different algorithms that we have in the sklearn arsenal. Okay. And then what we do, we try to tune the hyperparameters for these different algorithms. So when we are doing a gradient boosting, we try to tune the hyperparameters for gradient boosting. In this case, we did that. We use grid search CV for doing that. So we try different n estimator values, n estimators 1, n estimators 2, 3, 4, 5, 6, 7, 8, 10, 100, 1000. We take different values of n estimators. And by taking different values of n estimators, you're trying to find out what is the best n estimators. And once you narrow down, once you get that n estimators 31 is the best, what we do? We build a full model using n estimators 31. Okay, all right. Be very careful when you're using generative AI. because if you're using Colab, I mean, it can be very embarrassing if you're sharing this code with somebody, like, I mean, I just wanted to let you know, whenever you generate code, know that you get this kind of thing called generated code, right? So just be aware of this, okay? So, I mean, so whenever you're using prompts to generate code, if you're using Colab's, Gemini features to generate code, you will get this thing, right? You see this thing? So this will not go away, okay? Just be aware of this thing. Yeah. So if you're generating code, be aware of this thing. And this is the concept that is not only applicable for classification, you even have this for regression. So the idea is very similar even for regression. Just wanted to let you know. So this idea is applicable even for regression. Even for regression, this idea is applicable. Okay, so please keep this at the back of your mind. You have this idea even applicable for regression. Okay. So what I want to do now is I wanted to share a similar data set with all of you. Very similar use case I will share with all of you. This is on classification, but I'm taking a slightly different use case now, a slightly different use case, but based on classification itself. But the reason I'm taking this data set is to show you that how you can build like, how on the same kind of thing we can build a better model. Okay, if the data is better, how you will get a much better quality model. Okay, but the core ideas are very similar. This is the cancer data set basically. It's a very real world data set from the Wisconsin, you will see Wisconsin cancer data set is what we have here. So I've shared a PDF file that talks about how this data was collected, what kind of things happen behind the scenes, how we took the data. Okay. And then this is the actual data set. Okay. The Wisconsin breast cancer.csv. You have different features of the cancer cells. Okay. You can see that starting from column C, these are all the different features of the cancer cell, C, D, E, F, G, H, I, all the way. So we have actually analyzed every cancer cell under the electron microscope, and we have identified the different features of a cancer cell. So these are the different features of a cancer cell, the X as we call it. And based on this, we are trying to predict the diagnosis, the Y. So diagnosis can be B, benign. Benign means it's not, it's harmless. Or M is malignant. That means it's harmful, is dangerous. So this is the classification that we are trying to do. So you can ignore the ID column. ID is an identity column. You can ignore that. But the objective here is we are looking at the different features of a cancer cell to predict its diagnosis status. It's either benign or malignant. Okay, the approach is very similar. I mean, we are solving it the same way. You can see that this is our data set, and I mean, so we have the features, we have the diagnosis, this is the Y, and we are solving the same way. And I wanted to share with you a couple of things. First thing, the pair plot. Very interesting. It's a huge pair plot, I know. It's a very big pair plot, you can see. If you take a look at it, one of the first things that will come to your mind is that we are seeing a much better separation between the classes, right? If you compare this with the Pima diabetes one, the Pima diabetes was overlapping. Okay, the classes were not that well separated. So the data was not good. But if you look at the cancer data set, the data is a very good quality data set. For example, if you look at the radius feature, we are seeing a very clear separation between the classes, isn't it? Look at this. Look at the kind of features we have here. If I just show you one other example, look at this feature. Look at this feature called points first. Look at this. Look at how clear the separation is. And why is it important? Why am I talking about this? Because if you have a better quality data, this will give us upwards of a 90% accuracy straight away. And after that, if you further tune the parameters, use a better algorithm, you will get better results. But this is the important part. You look at a data set, you frame the problem, you look at the data, you look at the pair plot, you look at your feature importances, and at the first glance itself, you should know that, hey, I think I will get very good results here. I'll get very good results here. That's the idea. If you take a look at this here, these are very good quality features. In fact, if you look at the radius mean feature, I was talking about the radius feature. I think it's logical, because if the radius is more, the person is more prone to have malignant cancer. Orange. The higher the radius value, the person is more prone to have malignant cancer. you're more prone to have the orange color. And if the radius is less, you're less prone to have the orange color. So radius is actually a very, very important feature, isn't it? Like if the cancer cell is bigger in size, it's more likely to be malignant, else it is more likely to be benign. So that's the inference we are able to make. So the cancer cell is actually like you can take a look at it here actually. So this is a good data set actually, right? So lots of features. There are features which are bad. Like if you see like somewhere here, these are poor quality features. There's no separation. So when I do the feature importance, these are the kind of features I should drop. This is what will contribute to the noise in my data. So there are 31 features we have overall. So out of these 30 odd features, 30 features we have. So out of these 30 features, maybe 5, 6 are very bad features. We should drop them. But the remaining features are good quality features. We should use them. That's the idea. That's the idea. Now, rest of it is very straightforward. We are going ahead and building the models. You can see this is the baseline logistic regression model I am using. This is something we already discussed. Nothing much to talk about. And with a straightforward logistic regression, I'm straight away getting 93% accuracy. And the reasons I talked about. The reasons I talked about already, because the data itself is very good. If you look at your data, you're able to very clearly visualize a very good separation of the classes. So the class separation itself is very nicely visualized here. Right? That's why when you are using these algorithms, you're able to separate it out very accurately. Because remember, classification, you're ultimately trying to separate the classes. So we're getting a very good accuracy. And then we can use a pipeline, we can use other algorithms like decision trees. We're doing slightly better, 94%. False negatives are 0. This is very good, right? 0 false negatives. You can see that it's an excellent model we're getting right now. And then we can do grid search CV for hyperparameter tuning. So we talked about this. We can tune the maximum depth of the model. Okay, so all these are very, very similar to what we talked about. Okay, this is like seeing a validation curve for a random forest model. Remember, the hyperparameter value for a random forest is n estimators. Okay, this is the tuning knob that we are trying to tune, right? And you can clearly see that when the n estimators value is less, the model seems to be very underfit. The training and validation scores are very low. And when the estimator's value increases, we get to an overfitting zone. Okay, so lower the estimators, we can see the model is underfitting, and higher the estimators, we can kind of say the model is kind of overfitting. That's the inference we can make out of it. Okay. Okay, great. This was the cancer case study. So this is again fairly academic. I think the whole idea of until this part of the exercise is to really give you an understanding in terms of what is classification. There is another half an hour to 45 minutes discussion I will have with you in terms of some other algorithms. Like, as I said, decision trees, what exactly is it? What are some of the other algorithms that we have? We'll give you a brief understanding of that. And from there, we will do more real world case studies. Okay, so we'll get into more Kaggle based real world case studies in the next phase of our discussion, so that you get a very, very good practical sense of what is going on in classification. So that's going to be the plan going forward.